So entering Module 12, we're going to talk about exponential and logarithmic functions. The first thing we're going to do is find the inverse function for this exponential function that's given here. And the inverse, we just did that in the last module, inverses occur when you switch x and y. So in order to find the inverse, we're just going to switch x and y, and that leaves us with x equals 2 to the y. So you'll notice with what we started, we had y equals 2 to the x, our independent variable, or what we usually use as our independent variable x, is in the exponent of this expression, right? So this is an exponential expression. And when we switch x and y, we have found the inverse of the exponential expression, which is really a logarithm written in exponential form. So this notation can be converted and we can write y equals log base 2 of x. Okay, so we are going to talk about exponentials and logarithmic equations and functions in this section. And the one thing that we know is that exponential and logarithmic functions are inverses. So let's talk about the graphs of some basic parent functions for exponential and logarithmic functions. So we have an exponential function here, f of x equals 2 to the x. So some key points on that very basic parent graph. If I were to plug -1, 0, and 1 into my x, I would get these outputs 1/2, 1, and 2. And so what that looks like on our Cartesian plane here is we end up with a graph that is curving up. All right, and one thing we'll notice as we examine this more is that it has a horizontal asymptote right here at y equals 0. So you'll notice that these two functions we have stated are very similar but different. And if we talk about this 2 versus the 1/2, these guys are called the base that's raised to a variable exponential power. They are reciprocals of each other. So we have a positive 2 and a positive 1/2 as those bases. So what happens when I start to raise 1/2 to those same independent x values? So if I use 1, -1, 0, and 1, 1/2 to the -1, that flips that fraction, becomes 2. 1/2 to the 0 is 1. Anything to the 0th power is 1. And 1/2 to the first is itself. So you'll notice that those output y values are the same, but they're occurring in the reverse order. And what does this mean for the way our graph looks? Instead of increasing from left to right, now our graph is decreasing from left to right. And really, when I think about drawing this, it should curve up a little bit faster. Okay? So those are what exponential graphs look like, and both of them have that horizontal asymptote at y equals 0. So considering what a logarithmic graph looks like, we just said that logarithms are inverses of exponential functions. So that means this log is the inverse of that. And inverses occur when we switch x and y values. So switching our x and y values, we'd have 1/2, -1, 1, 0, and 2, 1. And if I think about plotting these, notice that all my x values are positive. So what we end up with here looks roughly like this. And this is my logarithmic graph that is the inverse of the very first exponential function we graphed. And one thing we remember we talked about in Module 11 is that inverses their graphs are going to be a reflection over that identity function y equals x. So logarithmic graphs will have a vertical asymptote at x equals 0. And so also notice the base 2 on both of these was a value bigger than 1. And having that positive base, notice that both of my graphs are increasing from left to right. They rise as we travel from left to right across the page. So the last part we'll graph here will be log base 1/2 of x. And these are also going to be the inverse of those original points for our 1/2 to the x power exponential function. So in order for me to do this, I'm just going to switch those x and y values as I list them. So I have 2, 1, 1/2, -1, 0, 1. So I took these original exponential x and y values and I switched x and y, interchanged my x's and y's to get this set of inverse points. And what this looks like is the inverse or the reflection of that previous exponential graph with the same base. So I have 2, -1, 1, 0, and 1/2, 1. And we get a graph that's shaped like this. And again, this one also has a vertical asymptote at x equals 0. So even though we don't know a whole lot about logarithmic graphs or functions, and the same with exponential, we've managed to determine that they're inverses and develop their graphs. So remember, we have two graphs of exponential functions on the left and two graphs of logarithmic functions on the right. Exponential functions are in the form of some base, a, which is raised to an x. Logarithmic functions, we read that as log base a of x. Okay? So in both of these situations, when we think about that base a, one thing we know, we'll say that a is the base. A has to be positive, and a is not allowed to equal 1. So that is our base. And if a is a value that is bigger than 1, then we're going to have a graph that is increasing, which means it's rising from left to right across the page. And if we have a graph with a base a that is fractional between 0 and 1, we will end up with something that is decreasing from left to right. And thinking back at these graphs, as I said, in the graph 1 and 3, my base is 2, which is bigger than 1. The graph rises from left to right across the page. Whereas in graph 2 and 4, my base is fractional. It is between 0 and 1. And don't be confused with the fact that 5/4 is a fraction. 5/4, though, is not between 0 and 1. 5/4 is 1.25. It is greater than 1. So these are both fractional between 0 and 1, which means they're both falling from left to right across the page. All right, so the domain in each of these situations. So for both of our exponential graphs, graphs 1 and 2, the domain is all real numbers, and the range is 0 to infinity. And notice I'm not using a bracket at 0 because we can't touch 0. There's a horizontal asymptote there. And if we think about our domain and range for these two logarithmic graphs, the second two on the right, you'll notice the domain is 0 to infinity and the range is all real numbers. So we don't travel left and right forever because we have that vertical asymptote stopping us at 0. So it's 0, not inclusive, to positive infinity. But the graph does have a vertical span from negative infinity to positive infinity. And we said that logarithms and exponential graphs are inverses of each other, and inverses occur when we switch x and y. And you'll notice in both of these situations that the domain, the set of possible x values, and the range, the set of possible y values, have also both been interchanged. Exponential functions have a horizontal asymptote at y equals 0, where logarithmic functions have a vertical asymptote at x equals 0. Again, the x and the y are interchanged. And then we've got some basic key points that we talk about. So for exponential graphs, we have -1, 1 over a, 0, 1, and then 1a. Whereas a logarithmic graph, those are all going to be interchanging your x and y. So I have 1 over a, -1, 1, 0, and a, +1. And that's not to say these are the points on any exponential or logarithmic graph. These are just on the parent functions. And the parent functions vary depending on what value you have for the base. Log base 5 of x would look very similar to log base 2 of x, but they're still a little bit different. So that a value can change these points. And then, of course, we can apply transformations. We can shift left, right, up, down. We can stretch or compress vertically or horizontally. And we can have reflections over the x or y axis. So all of these are subject to change. All of these properties we've written in our table. But these are just the properties for the parent function, the most basic exponential and logarithmic function we can determine.